Good morning, everybody. My name is Andrew Holmes, and I have the pleasure of chairing this session on energy materials. The first speaker is Osman Bakr from KAUST. He's a highly cited scientist and a founding member of the faculty. Would you please come and give your talk? Engineering the Future of Photovoltaics, the 16-year revolution in perovskite solar cells.
Thank you, Andrew, for this generous introduction. I'd like to thank the organizers for inviting me here today. It's such an honor to be with a panel of distinguished colleagues and as well as a distinguished audience. So today I'll be telling you about our work on perovskites, as well as how perovskites have evolved over the last 16, 17 years to change the face of photovoltaics. So as of now, solar power still forms a small, renewables and solar still form a small part of the energy mix, but somewhere in the last couple of years, there's been an inflection point where the cost curves of solar energy has become very favorable for its adoption, its rapid adoption, and now we're seeing really quite a fast rise in solar power, and it's expected to provide 70% of all renewable energies over the next few years. In fact, if we look at basically projections up to 2029, we're going to see that solar power is going to more than double from now, and we're going to reach about somewhere around 7 terawatts, and that's about 17 billion panels, and roughly covering 30,000 square kilometers. At the moment, the main technology in solar is silicon, and its costs have been going down significantly, but the question is, why do we need to keep improving? And the answer is that at the moment, silicon is quickly reaching its theoretical limit. That's called the Shockley-Queisser limit, theoretical limit of converting solar power into electricity. For a single junction silicon cell, it's about 29%. And we need to find ways of going beyond that, as well as there are other efficiencies that are in the process. Silicon is very energy-intensive material to make, and we need to find ways of making it at a lower carbon footprint, making solar panels with a lower carbon footprint. And that's why research in perovskites could play a big role. So perovskites, they're a bit different than silicon. They're a semiconductor as well. They're an ionic semiconductor. But although silicon's been studied much longer, just recently, power conversion efficiency of perovskites have exceeded silicon, at least in the lab scale. And in theory, the cost per watt of making a perovskite solar panel seems less. Okay? However, there's a lot of challenges with making perovskites, and we still expect silicon's cost curves to drop and to decrease. But the advantage still of perovskites is significant and potentially transformative to solar technologies, especially when we think about in terms of weight, so specific power. Perovskite solar cells are thin film solar cells, so their mass, the mass per power they produce is much less. So that makes them really attractive for space applications and applications that require high power densities. As well as perovskites can play a very big role in improving silicon technology itself, because perovskites can work in tandem with silicon to improve the efficiency of the overall system. So in the last 17 years, perovskites have gone from about 3% efficiency all the way to 27%, and that took silicon about 60 years to achieve this kind of efficiency. And perovskites, there's multiple types of perovskite devices. There are polycrystalline devices and there's single crystal devices, and each one of them is going through a different transformation. Silicon is a single element material, but perovskite is an ionic compound. There's at least 3 elements involved, 3 components actually. So perovskites have this ABX3 structure, where B is in an octahedra surrounded by X. So and typically A can be a cation that's such as cesium or methylammonium or formamidinium, so it can be organic or inorganic. B is usually lead, but increasingly we're seeing tin being introduced. The X is the halide, and it could be iodide, bromide, or chloride. And as long as the relationship between the different components, the radii of the different components obeys this tolerance factor. This tolerance factor would be equal to 1. There's a high chance that we'll form a perovskite structure. What makes the perovskite structure very interesting, it has tunable band gap, so you can change by just changing different components of the system. Very simply, you can change the band gap. It has very high absorption coefficients, and as well as defect tolerance and long charge carrier diffusion lengths. The perovskite solar cells, the basic principle of the way they work is perovskite layer absorbs photons, they get the excitons form, and they travel to their respective to either the electron extraction layer or a hole extraction layer, and a separation occurs, and basically each electrode collects its respective charges. Okay, so it's a simple structure, but it includes multiple components. Not just the perovskite is important, but the electron transport layer, the hole transport layer are important, and their interface where the charge transfer occurs is very critical. Perovskites also have not just a single form. Typical form we see is a 3D perovskite, but if we start introducing larger A-site cations, we can start breaking up the perovskite into 2-dimensional layers, or even 1-dimensional layers, or even 0-dimensional quantum confined structures. By simply varying the halide composition, we could change the band gap of perovskites. That's what makes them very tunable and very useful as materials in solar cells, especially tandem solar cells, because we could tune the band gap very readily. So we have multiple levers for controlling the band gap, either by controlling the halide composition or controlling the A site composition. And in fact, also the B site as well. What makes perovskites kind of unique from most other semiconductors, compound or silicon, is that in silicon type semiconductors or other 3-5 semiconductors, because the conduction band and valence band are formed from bonding and anti-bonding states, whenever you have a defect where they're dangling bonds, the trap state that forms within the band gap, and that leads to a deep trap state that tends to quickly deteriorate the electronic transport properties. But with perovskites, because both the conduction band and the valence band have anti-bonding components, when you have a defect that forms, that defect is either shallow, close to the band edge, or in fact within the band valence band. And so it doesn't really, it's not really a stopper for charge carriers, but more of a speed bump, so to speak. And with perovskites, we could grow them into very nice big crystals that have very low defect densities, despite using very dirty chemistry and and growing them in lab conditions that normally we wouldn't expect high purity semiconductors. Compared to other emerging semiconductors such as polymers or CIGS or quantum dots, for example, perovskites have a much lower defect density or electronic defect density and have a much longer carrier diffusion length. So a few years ago, we measured the carrier diffusion length we managed to get the most definitive measurement of carrier diffusion length, and we found that basically in single crystal perovskites, we get a carrier diffusion that's close to 0.5 millimeter, whereas in all the other semiconductors, it's either micron or below. In some cases, it's just a few hundred nanometers. So this very long carrier diffusion length really makes it possible to make very thick perovskite devices, and I'll explain at the end why it's important to have. There's some very significant applications for thick perovskite and thick solar cells. However, this defect tolerance, also in the ionic nature of perovskites, leads to formation of many types of point defects. Even though they're electronically benign, they can actually eventually lead to the rapid chemical degradation of the material, especially when they interact with temperature, bias, and light, and all these things come together. They can lead to the degradation of the compound and phase segregation, and eventually the breakdown of the device. Just to give you a bit of a historical perspective, say the first significant applications of perovskites in devices happened when David Mitzi introduced, tried to apply perovskites, two-dimensional perovskites in transistors, and then from that point things were quiet until in 2009, Miyasaka started using perovskites as substitutes for dyes in dye-sensitized solar cells. That first iteration of the solar cell only lived for a few seconds, I guess, and was very fragile. Eventually, Park and Gratzel replaced the liquid in the dye-sensitized solar cell with a solid state whole electron transport layer. And then another big step happened when Snaith and co-workers identified perovskite as an ambipolar semiconductor, which kind of distinguished it as a category on itself from dye-sensitized solar cells. I think our biggest contribution to the field happened when we started showing that large single crystals of these devices, of these materials, can be grown in very simple fashion and still maintain a very low defect densities comparable to optoelectronic silicon. This was surprising because back then people thought diffusion lengths in perovskites were around a few hundred nanometers. We showed that it was in the tens of microns at least. And now, as we speak, perovskites as single junction devices have reached 27%, but now we see the big opportunities in tandem cells where you could create multiple layers of perovskites or combine perovskites with silicon to get devices that reach between 30 to 35% efficiency with a potential limit of 40%. If you look at perovskite field, there's typically 3 types of devices, configurations. One of them is called PIN, where the whole transport layer is closer to the transparent oxide layer, and the electron transport layer is on the other side. And you have the NIP, where the electron transport layer is closer to the transparent conducting oxide. And then you have single crystal devices as well, and tandem devices that combine multiple layers of perovskites of different band gaps to collect photons of different energies more efficiently. When the field started, NIP type of devices were dominant, but over time, PIN devices, because they were more stable and there was a lot more flexibility in engineering their interfaces, they advanced much faster in terms of stability, and now they've even exceeded NIP in terms of efficiency. So far, the most dominant structure in perovskite, the perovskite field has been the PIN because of the stability milestones it's achieved and its ability to integrate with tandem solar cells. There's a lot of opportunities now in the perovskite field where they need to be addressed, not just only integrating them into tandem cells, but also improving their stability and scale up, which is attached to the interface engineering and processing. So there's actually a lot of ways to you'll see the field is very rich with ways of addressing interface and interface challenges in the device. So here's one example that we did where we basically used small methylammonia, some small alkyl ammonium cations to passivate grains and kind of control the grain orientation in devices. This showed that by controlling the grain orientation in devices, you could significantly improve the efficiency and stability of the device. You also were seeing now a lot of work on aligning the energy work functions of the different layers, because you want to maximize charge extraction. And so you have to be able to control the interface between the perovskite and the electron transport and hole transport layer very well. And we're seeing now that methods being used to introduce also additives that could in situ control the work functions of the perovskite layer and align them with the work functions of the Fermi levels of the electron transport layer and hole transport layer. And that leads not just to better efficiency, but also promotes better electron extraction and stability. There's also big challenges in terms of fabrication of the device. At the moment, all the champion devices that are being produced, they're made through a method called spin coating. And spin coating is a process that allows you to make small devices, but it's not really scalable to larger area of fabrication. And for perovskites to be commercially viable, we have to develop ways that make its manufacturability simple. And so one area is blade coating, but what people are finding out is that the crystallization kinetics in blade coating is very different. And so the processing of these devices requires some different modeling and different ways of looking at than simple spin coating. And here's an example as well of what we've done in controlling the interface, not just between the whole transport layer and the perovskite, but also between controlling how the transport layer itself can interact with the perovskite. And here we replaced what used to be C60, we replaced it with an ionic form of C60 that connected better with the perovskite. This gave the interface mechanical stability and improved the stability of the device against delamination, and gave thermal effects. So, one area that my group focused a lot on is in single crystals, and we were very interested in understanding how to grow single crystals, understanding the properties of the devices, because when you look at polycrystalline films, it's really difficult to distinguish the properties of the material itself from the properties of the grain boundaries. And so this was, we spent a lot of time doing that, but also figuring out not just how to grow crystals that have high quality, but how to grow them quickly in order to make them practical. So typical ways of growing crystals, either through cooling or through anti-solvent methods, requires weeks to do. And what we've done is we've discovered a method that allows us to grow the crystals within hours. And just to give you an example, for a crystal that normally would take a week to grow, basically we found a way of initiating supersaturation in the solvent through a method called inverse temperature crystallization. And this allows the crystals to grow at a very rapid rate, and allows us as well to control the shape of the crystal. And that's very important, because then you could start putting the crystals between two different layers, an electron transport layer and a hole transport layer, and make a single crystal device. And so what surprised us is typical perovskite films were a few hundred nanometers, but we grew crystals that were 100 times that thick, and we still obtained very efficient devices. And this got us to think, so we spent a lot of time working on single crystals, and because the charge diffusion length in perovskites were so long, we were able to make single crystals that ranged anywhere from 20 microns to 100 microns that were still almost as efficient as thin film devices that were 100 to 700 nanometers. So that was very important for us, and I'm not going to go too much over the different device configurations that we've done, but we've found ways of growing crystals without volatile organic cations and improving their efficiencies and their stabilities over time. Now I'm just going to go quickly over, just to tell you a bit about tandem devices. There's now two kinds of tandem solar cells that are, there's silicon with perovskite, and there's tandems, there's perovskite with perovskite tandems. At the moment, silicon with perovskites seem very interesting because they integrate very well with current technology and current manufacturing methods. However, we believe over time, perovskites are going to win out, because they use 1/4 of the energy input to make, and their potential for their limit for efficiency is much higher. So we see that this is a very hot area that with perovskite, there's a lot more to do, but the potential is much larger. I'm just gonna quickly, because in the interest of time, what makes perovskite very interesting is that it's not just about we can make multi-junction solar cells that go beyond 2 junctions. That's because we could control as well the composition and band gap of each perovskite layer. And that means, in theory, we can start looking at efficiencies that can potentially get close to 45 to 50%. And so that would be very exciting for applications that, like space applications, or applications that require very high energy density. If we want to make perovskites commercially viable and widely adopted, we can't just focus on efficiency, and even not just on stability. We have to look at the whole life cycle of the device, and we have to think about how we're going to recycle different materials, how we're going to mine the different elements, specifically things like cesium and indium. Indium is in the transparent conducting oxide. Cesium is in the perovskite itself. These are not that common of elements, so we need to figure out how to recycle them and use them, and over time create a closed loop that doesn't damage the environment. It creates the least amount of footprint in the environment. I also would like to point your attention to this paper that I recently read on comparing the evolution of perovskites to the evolution of CIGS technology, copper, indium, gallium, I think sulfide, base or selenide, and basically these are solar cells that are also that have gone into the evolution of their own. They became relatively efficient. Their adoption slowed down quite a bit because of the complexity of the composition. There were a lot of elements involved in device stability, and that meant that in order to achieve device stability, you had to deal with the system overall, not just optimize one parameter and leave the rest and optimize things separately. So there's a lot of important lessons for us to learn from CIGS system that we need to apply to, that could be applied to perovskites. Overall, I mean, just to give you an idea, in perovskites, typically when people measure stability, they look at either illumination, bias, or thermal stresses. Unfortunately, these stresses interact with one another, and when they do interact, they generate complex degradation pathways, and so really we need to study them together in order to create a solution that addresses the stability. In a real environment, you're going to face thermal stresses, you're going to be facing biases, electrical biases, as well as UV and photo-generated stresses and degradations. So before I close the chapter on the perovskites, I just want to say that it turns out that even though we're going through this transformation in the PV field, perovskites are already changing. They're already reaching commercialization when it comes to high energy radiation detectors, X-rays and gamma rays, and they're already making big transformations in this field, because thick perovskite solar cells and devices, in fact, are very good X-ray and gamma ray detectors, and that's really changing the way we do things, reducing the cost of medical imaging and even high energy studies. So this is where I think already the fastest commercialization and adoption is happening in this area, and where research on solar cells has led to significant improvements in an adjacent field. Before I conclude, I just want to just discuss something that we're doing on maybe on the commercial side to address the bigger problem in solar. If you think about it, we're going to have by 2029, 2030, we're going to have 17 billion panels, and there's no way for how are we going to maintain this infrastructure? How are we going to maintain 17 billion panels? And right now, a lot of things are done manually, but there's a lot of issues when you try to install panels that could lead to damage. And during the installation, the weather effects, aging, all these things actually are what we're finding is the panels behave differently than when we do the aging tests in the lab. And each region, whether it's in the Gulf or in the US, each region has its unique issues of degradation and damage. Surprisingly, the common methods for testing damage, visual and thermal, only detect less than 20% of the damage. So we miss 80% of the damage with current methods. And the only method that allows us to look at the real damage that happens is called electroluminescence. And that normally requires you to take the panel and to a lab and get it tested. And so what we've done is, this is something we've commercialized, technology we developed in our lab, where we squeezed the imaging technology required to do electroluminescence in a lab. We put it on a camera that can be placed on a drone. And then, in fact, instead of doing the testing in the lab, you could start doing the testing in the field. And so basically, this is how it works. Now instead of dismantling the panels, you can just fly the drone, and you could easily just electroluminescently image the panels and see the damage that in the past was not visible to thermal and visible. And you could at the same time classify it. In fact, we could catch damage that's caused by weather events like hailstorm cracks, or even damage that's caused by manufacturing and installation. And that starts informing the industry on how best practices for installing and maintaining facilities. Before I conclude, I'd like to thank my group members for really doing over the years outstanding work, that much of it that I've shown you today, as well as tremendous collaborators, specifically over the years, Ted Sargent from Northwestern, Kai Zhu from NREL, and Omar Mohammed at KAUST. There are many other collaborators that I've worked with over the years, but for this specific work, these folks have been instrumental. And also, I'd like to thank our funding. Most of the funding came from KAUST, but also a lot of significant funding came from Aramco. And our work is anchored in, we have a center of excellence at KAUST called Center for Renewable Energy and Storage, and we're doing groundbreaking work when it comes to energy storage and renewable energy generation. I want to thank our colleagues for listening here today. I told you about some of the things, the evolution of the field, and basically what we've done in the past and what we need to do in the future to make solar adoptable, specifically perovskite technology, transformative, and allowing us to really create renewable energy that adopts at a much faster curve and scale than it is right now. Thank you for listening.